Welcome to topic 9.4. We're going to work on what's called percent composition. On its own, percent composition has an important aspect in terms of chemistry in the industry. If you're looking for a source of iron or a source of oxygen or a source of water, for example, knowing the percent composition of different compounds help decide which compound may be more useful as a source over something else. But percent composition lends itself to our next topic, which is the empirical formula. We are going to take a little bit of a break from conversion, so you're probably relieved for that. So we're going to take a pause for a minute and move on to what's called percent composition. Pretty much percent composition is no different than a percentage you find in your math class. So if you want to know what percentage of your class is made up of juniors versus sophomores, you would need to know how many kids are in your class. You need to know how many juniors, how many sophomores, and then you can find that proportion or ratio to determine that. And basically that's the same thing we're doing for a compound, is we're figuring out what is the percentage of each element that makes up that compound. So to find the percent composition, you need to know the molar mass of that amount of element in the compound compared to the molar mass of the whole entire compound. And the one thing that oftentimes gets forgotten and confused, and I haven't really figured out why, is you need to take something times 100% to convert it to a percentage. And so the first example is working with copper 1 sulfide. So these are kind of the step-by-step process of what you need to do to get to that final answer of knowing the percent composition of this compound. So the very first thing that you need to do is you need to know what is the chemical formula. We see that we have copper 1 sulfide, so that means that copper is Cu with a +1 charge. We know that sulfide is sulfur -2. Crossing charges, the correct formula for this material is Cu2S, and you've just completed the first step. Now, essentially what we're going to do is figure out of this compound what percentage of this is copper versus what percentage of this is sulfur. So to do that, we need to basically do molar mass for the compound, but I'm going to have you guys do it slightly different than what we did before. We're still going to list things out. So we have copper, and we have 2 of them, and we have sulfur with 1 of them. You're going to look up their corresponding masses. So sulfur is the 32.07. And so instead of getting a grand total, what I'm going to have you do is get 2 separate totals for each part of the compound. So copper is 63.55. So when you multiply that by 2, you get an answer of 127.1 gram per mole. And we get that sulfur is the 32.07. That's going to save us a step here in just a moment. So again, what I would like you to do different from what we've done with molar mass in the past is we've just calculated and added it all up and got 1 total. Go ahead and find the molar mass of each individual piece or each individual element within that formula. Now, the next step is you want to know the molar mass of the whole entire thing. So now what we're going to do is add these 2 up to give us the grand total molar mass of the entire compound, which gives us 159.17, its molar mass, so grams per mole. And that's of the Cu2S. So basically we've done now all of the groundwork, and now it's basically plugging into formulas. Like I said, we have 2 steps. So I'm going to try to color code things. If you haven't picked up on it, I like color coding things. So everything related to copper, I'm going to do in this pink color. So the first thing we need to do is find what percentage of that compound is Cu. So I like to start by putting %Cu as my unit of knowing what in the world I'm solving for. So we're looking at, of this whole entire molar mass, how much of it is made up of that copper? Well, we know of this mass, 127.1 grams is copper out of the mass of the compound, 159.17. So I can see that easily the majority of this compound is made up of copper. Again, you multiply by 100. This is the one thing I cannot figure out from year to year. So these cancel. And so what you're doing is taking 127.1 divided by 159.17. You're limited to 4 sig figs. You times by 100. Percent is a unit. Do not type percent on your calculator. I don't get, again, where that confusion falls in. I don't know if it's a difference in how math uses percentage versus us, but it really should not be different. Percentage is a unit, no different than grams per mole. So off of my bandwagon now, when I go ahead and plug that in, divide it out, and solve, I got an answer of 79.85% copper. And that's my final answer for that piece. I have a second piece because I have a second element. So I'm going to work this through in my blue pen for sulfur. So we have percent S. It's part of the whole. Sulfur's component is the 32.07 out of that whole mass of 159. So I can see that it's very little. Times 100%. Getting back on my soapbox. Grams per mole cancel. Do not put percent in your calculator. It's a unit. So again, when you work it through, you can keep 4 sig figs because of the 32.07. You get a percentage of 20.15% sulfur. Now, the one thing that's nice is you can check your work. All percentages add up to 100. So if we add these up, and I can't remember how this one falls. Yeah, it should work out. This one comes out right to 100. Now, usually I use like a rule of plus 1 and minus 1%. So if you get somewhere between 99 and 101%, I would say that you're good. Some of it turns into how numbers round and counting sig figs, that it can throw your percentage off, so it doesn't always land exactly on 100% each and every time. So I have a second practice problem that works with percent composition with magnesium nitrate. I would highly encourage you pausing the video and trying to work it out for yourself. So the first thing you need to do is you need to get a formula. Magnesium nitrate. Magnesium is Mg plus 2. Nitrate is NO3 minus 1. Therefore, it is Mg NO3 2. That was the first step. In the next part, it told you to find your percentage of your each element in it. So we have 3 elements to find in this particular problem. We need to find magnesium. We need to find nitrogen. And we need to find oxygen. Working it through. Magnesium, I have 1 of them. According to the periodic table, its molar mass is 24.31. Making that easy, it's 24.31 grams per mole in this compound. Nitrogen, looking at it, it distributes in, so I have 2 of them. According to the periodic table, it's 14.01. Doubling it, you get 28.02 grams per mole. The last one, oxygen, that 2 distributes into the 3. Therefore, we have 6 oxygen. Its molar mass is 16. Multiplying those up, the total there is 72.06. So the next thing you need is you need the molar mass of this whole entire compound. You get that by adding these 3 up. So the molar mass of magnesium nitrate is 124.39 gram per mole. And again, I got that by just adding up my 3 individual elements within the compound. So like the next problem, or the last problem, we're on step 4, where we now need to find our individual percentages. So I'm going to start with percent Mg. Again, it's the part out of the whole, so its part of the mass is 24.31. The whole being the molar mass, so 124.39 times 100%. Again, grams per mole cancels, times by 100%, keeping it to 4 sig figs. We get an answer of 19.54%, and include what it is. It's magnesium. Your next step then is nitrogen, so percent N. Its part is 28.02. The whole stays the same, the molar mass of 124.39. And we get a percentage of the nitrogen as 22.52% N. Last but not least, percent O. We said its portion was 72.06. So we can see that this compound is very rich in oxygen. Times 100%. So we get an answer of 57.93, which should make sense because it eats up so much of the molar mass. Again, and I think this is one that does that, you can double check your work. So 19.54 plus that 22.52 and that 57.93. Yeah, so this one comes out to 99.99%. I would call that good because, again, some of it's my sig figs and rounding. So that is how you find percent composition of a specific element in a compound. Now, hydrates have a way of being useful for a source of water. So some compounds, when they crystallize, and I realized I grabbed two of them, when they crystallize in their three-dimensional structure, there's these gaps and spaces, and water gets trapped within them. And so one compound that does that is sodium carbonate. It can form a hydrate where 10 water molecules get trapped for every one molecule of sodium carbonate. So two important terms, a hydrate and anhydrous. A hydrate means that it's basically a salt. So sodium carbonate is a type of salt because it's an ionic bond, and you have water trapped within it. So the prefix "an" means without. So anhydrous means that you've heated it up, boiling the water out, and you've dehydrated that hydrate. Guess what? You can rehydrate it. Add water to it. When it recrystallizes, it will have those water molecules trapped within. So what I'm going to do is show you how you figure out what percentage of a compound is made out of water. This becomes really useful for things like looking at how we can move on to other space exploration and sources of maybe potentially taking water with us and things of that nature. So it says write the percent or find the percent composition of water in sodium carbonate decahydrate. So I haven't taught you hydrate naming because I've been waiting for us getting to this part. So we know what sodium carbonate is. Sodium is Na plus 1. Carbonate is CO3 minus 2. Therefore, we get Na2, CO3. Okay, so how we show water is we show a multiplication sign as a dot, and we do decahydrate. So deca means 10, hydrate means water. So we show it as a coefficient 10, H2O, and that's what sodium carbonate decahydrate looks like. So overall, there's some similarities, and then there's a couple of differences as well when it comes to how do you work these out. So it tells you to find the mass of the water present in the compound. So essentially what you start with doing first is you find the molar mass of H2O, understanding that it contains 2 hydrogens and 1 oxygen. Hydrogen is 1.00 and oxygen is 16.00 according to the periodic table. Therefore, the molar mass of water is 18. That's for 1 mole of a substance. We have 10 moles because of this coefficient 10. So we need to include that we have not just 1 water molecule, but we have 10. So we're going to multiply that by 10, and so we get 180.0 grams per mole of our water. Now, the next thing is we need to find the molar mass of the hydrated compound. The hydrated compound is this entire piece here, the Na2CO3 with the 10 water molecules locked within it. So I'm going to go ahead and find the molar mass of my Na2CO3. So I have sodium, I have carbon, and I have oxygen. Let's see here. So then sodium is 22.99, carbon is 12.01, and oxygen is 16. So we're going back to our regular ways because we're not finding with hydrates. I'm not asking you to find these individual things. All I care about is what percentage of it is the water. So we're going to go ahead and get a grand total for the entire compound. When I do that, I get 105.99 grams per mole. and that's of just the sodium carbonate. I need to include that there is 10 moles of water included. So the last step is you need to go ahead and add that 180.0 grams per mole. So the grand total of this entire hydrate of the sodium carbonate decahydrate is going to be 285.99 grams per mole. So now we can figure out how much of this hydrate is water, how much of this mass. So you take the molar mass of the water, which is this piece here. So we're going to take 180 over the molar mass of the hydrate, the 285.99. Dividing these out, multiplying it by 100%, the answer comes out to be 62.94% water. Now, one way to really help check yourself is a lot of times students forget to include this water. If you did that, your answer down here, your number down here would have been 105. You would get a percentage greater than 100. You cannot have more than 100% water within a compound. You'll definitely never get something that's even 100% water unless, guess what? It's water. So we're not going to end up with numbers like that. So that's just one way to help check yourself is, again, you take the mass of the amount of water you have over the molar mass of the entire compound, including, in this case, the 10 molecules of water, and we got 62.94%. So one last example to show you hydrates is we have copper 2 chloride dihydrate. So to take care of the copper 2 chloride, copper is +2 in this scenario, chloride is Cl -1. So the formula is CuCl2. Dihydrate. Dihydrate means we have 2 water. So we show our dot to show that it's a hydrate, coefficient 2, H2O. Everything else is the same. We're going to figure out of this compound how much of it is water. So you start out in the same boat. We need to know the molar mass of H2O, and guess what? It's still made out of hydrogen, still made out of oxygen. We have 2, we have 1. Hydrogen is 1, oxygen is 16. The molar mass of water will always, always, always be 18. So the only difference, starting out the last problem to this problem, is we have a different number of water molecules. Different hydrates can hold different quantities of water. This one only holds 2. So we multiply this by 2 instead of 10. So 18 times 2 is 36. So the next piece that we worked through was figuring out what is the molar mass of our salt, the copper 2 chloride. So when you work through that, we have CuCl2. It's made out of copper, it's made out of chlorine. We have 1 copper, 2 chlorine. Chlorine is 35.45, copper is 63.55. So the grand total of just those two together gives us, and I'm going to just go ahead and add in my water now. So I'm going to go and include my H2O, which I said was 36. So multiplying and adding all 3 of these up, you get 170.45. So the important part on the whole, like you have to figure out your part of the whole, we have to include that water. So then percent H2O is the mass of just the water, the 36, over the mass of the whole, including the salt and the hydrate. That's that 170.45 times 100%. When you divide, multiply, and round to 4 sig figs, you get an answer of 21.12% water. So comparing the two, the sodium carbonate decahydrate is 62% water. So this is a much, if you're a chemist trying to find some water, not that we typically do this, but for different applications it can be useful. This is definitely a greater resource of water compared to water here. I'm not talking about this as a resource for drinking water, for example. All right, so that is percent composition. Let me know if you have questions.